Now that we've taken a good look at the solar system, we're ready to take a look at the rules of physics and different laws that govern the motion of the planets around the sun, or really any object that is in orbit around another object. And we call an object that orbits another object a satellite of that object. So the Earth is a satellite of the sun, the moon is a satellite of Earth, and of course we have man-made satellites like our weather satellites, the International Space Station, which are also satellites of the Earth. So a satellite is any object that's orbiting another one. And all objects in space are governed by the force of gravity and what we're going to be calling Kepler's laws when you go through and look at how they orbit here. And that's what we're going to be taking a look at in this lesson. First, we're going to look at gravity. So the force of gravity is the force that controls the motion of all objects in space. And in order to understand how these objects moves, we need to understand how gravity works. And gravity is simply defined as the force of attraction between any two objects. And we can see it in this diagram between the Earth and the moon. These arrows are basically what we call, force vectors. And we're seeing that the moon has a pull of gravity that is basically acting on the Earth, and the Earth has a pull of gravity that is acting on the moon. And the Earth's gravity in this case is going to be more dominant because it's a more massive object. And that's why the moon is orbiting the Earth and not the other way around. And this force of gravitational attraction between these two objects is balancing out the centripetal force that's trying to push the moon away from us, and that's why the moon is in a pretty stable orbit, basically staying in roughly the same spot. Although gradually the moon is actually getting slightly, very slowly farther away from Earth over time, but it's not something in your lifetime you will ever notice the difference of by far. And when we say a force of attraction between any two objects, that literally means any two objects that exist have gravity. So you have your own force of gravity. Your cell phone has a force of gravity. A rock has a force of gravity. And why when I go past a smaller object like my pencil that's sitting next to me on the desk, does it not just suddenly get attracted to me? Well, it's because the Earth has a much more massive pull of gravity and it is dominant. So the Earth's gravity is dominant in our neck of the solar system. The sun's gravity is dominant over the whole solar system, which is why the Earth orbits around the sun. So really the mass of the object and also the distance the two objects are apart become very important. If we could throw you into deep space and you were completely by yourself away from all other objects, and we gave you a small pebble and you threw it just right, that pebble would actually orbit you because your force of gravity would be dominant. You'd have your own, of course, you'd be so far out in space that, no one would ever see you again, but that's a different story. So let's go ahead and take a little bit more look at gravity here. Now there's an equation for gravity, and the equation for gravity is that the force of gravity equals g, which is a gravitational constant. It's a defined number. We're not going to need to worry about what it is, but it's just a number that's always going to be there. And that gravitational constant gets multiplied by the mass of one object times the mass of the other, but divided by the distance squared. And since the distance is squared, it's actually the most dominant factor in this equation. This is why as you leave the Earth and get into space, you start to get weightless because the distance is increasing, and that very drastically reduces the force of gravity. But notice the mass of the two objects are also important because those are in the actual equation too. So the force of gravity is determined by two things: mass and the distance between the two objects. So the mass of both objects and the distance between them. And these are relatively easy things for us to measure in space, which means that gravity is a calculation that's pretty easy for us to actually do. So as the mass of an object increases, the force of gravity increases. This is our first rule. Since mass is in the numerator of the equation, if either of these numbers increases, the force of gravity will increase. So as mass increases, gravity increases. Think to yourself, is that a direct or inverse relationship? And hopefully you figured out that it is a direct relationship. And that's important for you guys to remember. So more mass, more gravity. That's why the sun has the dominant gravity in our solar system, because it is the biggest. And the Earth is more dominant over the moon because the Earth is bigger than the moon. Now the next part is important too. As the distance between the two objects increases, the force of gravity decreases. So is this a direct or inverse relationship? Hopefully you realize it is inverse. All right, basically if you increase the distance, the force of gravity decreases. And mathematically that happens because distance is in the denominator. And it's also squared. So when you do that, you put a bigger distance in between, the force of gravity drastically decreases. Distance is a really important factor there. So how does this relate to objects that are in orbit? It turns out the speed of an object in its orbit, which we call the orbital velocity, that's a good word to know, it's just the velocity or speed that that object is orbiting. The speed of an object in orbit changes as the force of gravity changes. And basically, here's how it works. The stronger the force of gravity is, the faster the object will move. The weaker the force of gravity, the slower the object will move. Now, this little animation on the right is horribly not drawn to scale. It's not even close. So don't worry about the distances or the size of these objects. They're not accurate at all. But it shows us the relationship that we need to know. We're looking at Earth and we're looking at Mars. And you have to say to yourself, all right, well, which planet is moving faster? Well, the one that's moving faster is the Earth. And the reason for that is, aside from the fact that the Earth and the sun are, more massive than if we looked at the sun compared to, say, Mars instead of the Earth. Mars is not nearly as massive as the Earth. But the really important factor is distance. The Earth is closer to the sun, so the force of gravity is stronger. And that is why it's orbiting at a faster speed. Mars has a greater distance from the sun, so the force of gravity is much less between those two objects, and that's why it's orbiting slower than the Earth actually is. So the farther away you get, the weaker the flow of gravity, and the slower the orbit ends up being. That means it takes Mars a lot longer to revolve around the sun, which means they have a longer period for each of their seasons than we would on the Earth. And we've seen that with all the other planets. The farther away you get, the longer it takes for them to orbit. And the reason why is because of that weaker pull of gravity. So now that we're taking a look at the force of gravity, we can spend some time talking about Kepler's laws. And what we're looking at in this picture here is something known as the International Space Station. And this is really an impressive feat of engineering. And they call it the International Space Station because it really is truly international. The United States, Canada, Russia, Great Britain, Japan, China, everybody has basically contributed into the space station. Israel, Brazil, like you name it. Even countries that don't seemingly get along, we come together sometimes when it counts, and that's what happens with the space program here. And what's really interesting about this, too, is this picture on the right. You can see that the station's a lot smaller. In order to build and construct this in space, it's the largest construction project ever undertaken in space. They basically had to bring each part up one by one, the different components. So you can imagine a module like this and a module like this. And sort of like Legos, they had to link them and lock them together in space. They basically built it piece by piece, adding on different amounts each time, which is pretty impressive. These parts here are solar panels that power the station, and the living quarters are basically in here. And even since this picture was taken, there have been more parts and components added to the station. Now, the reason we're showing you this is a satellite of the Earth. This is constantly orbiting the Earth, and it's actually not very high. You can actually see the glow of the atmosphere in the distance there. When we say it's in space, it's really not in far space at all. It's actually really at the top of our atmosphere. But it is in orbit around the Earth, and that means just like any object in orbit, this is governed by Kepler's laws. If this station were moving too slow, Earth's gravity would pull it back in and it would basically burn up like a meteorite entering into our atmosphere. If this was going too fast, it would shoot off into space and escape Earth's gravitational pull. So there are very specific rules, Kepler's laws, that are followed, and of course a lot of other calculations that go into it, to basically assure that this is in a nice stable orbit. The same thing's true of all the planets, moons, and anything that orbits another object, whether it's a comet, an asteroid, you name it, they all follow these same rules. So before we go any farther, we just have to tell you that Kepler was a mathematician, so all his laws are kind of like reading a math textbook or some math document. So if you read the law at first and it doesn't make sense to you, don't worry. We're going to explain it in sort of normal terms that'll often make it a little bit easier. And the first law is really not too bad to understand at all. So Kepler's law number 1 says the orbits of the planets around the sun are ellipses with the sun located at one focus. And it doesn't have to be the planets. It could be a moon around a planet. It could be a satellite around another object. But in this case, we're going to focus on the solar system. So what we mean by an ellipse is not a perfect circle. Now, just for the record, this diagram is not at all drawn to scale. We exaggerated the amount that the Earth's orbit is stretched out, just so you can see it a little bit better for explanation. In reality, you would need a very keen eye to see the difference. But basically, an ellipse, you can think of it sort of as a shape that's almost like an oval. It's not a perfect circle, but it's not a straight line either. It's somewhere in between. So it generally has this kind of oval-like shape to it. And we say the sun is located at one focus. A circle has one point at the center, but an ellipse actually has what we call 2 focal points. They're kind of like the center points, but there can't be one of them because we have an oval shape. So there's 2 center points, and we call those focal points, or the focus. And the plural of that is called the foci. So anything related to that will be related to that same term. Now, the sun is at one of the focal points. The other focal point is just an imaginary point in space. There's nothing actually there, It's just what we call an imaginary point, but it is something that we can measure and reference off of. And then we're going to share a calculation in just a minute here, where what we actually do is to figure out something called the eccentricity to tell us how elliptical, that's the term to associate with an ellipse, how elliptical this orbit is. We actually have to measure something called the distance between the foci. Again, foci is the plural form of focus. So we actually can measure the distance in whatever unit we choose to use between those focal points. And then we're going to need another measurement, which is across the widest part of the ellipse, and we call that the major axis. And by having these two measurements, we can go ahead and calculate something called eccentricity, which we're going to go ahead and show you. So what eccentricity is, we brought back this diagram from before. It's defined as the out of roundness of an ellipse. Now, I know that's a little bit of a weird definition. Out of roundness is kind of not a very technical term. But basically, if you have an eccentricity that is equal to 0, you have a perfect circle. That would mean that your two focal points are one on top of the other, and you actually would get a perfect circle. If you have an eccentricity that is 1, you would end up with it so stretched out you actually would have a straight line. And most ellipses are somewhere in between. So the eccentricity is going to tell us how close that ellipse is to being a circle, or is it closer to being a straight line? And like I said, most things are going to be somewhere in between. So to calculate eccentricity, this is actually the last formula we're going to use from your Earth Science reference tables that we haven't shown you yet this year. You're going to take the distance between the foci. We're going to put that in the numerator. So whatever that measurement is between those two focal points, and you're going to divide it by the length of the major axis. It's a pretty simple formula. It's just those two numbers that are involved, and that is your equation for eccentricity. Again, you can find it on the cover of page 1 in your reference tables. It's just not nice and color-coded like this one. So let's do an example with an eccentricity question. The Earth's eccentricity is 0.017. So our question is the Earth's orbit almost a perfect circle or more like a straight line? And the answer is going to be that Earth's orbit is closer to being a perfect circle because 0.017 is closer to 0 than it is to 1. So we basically look at that value for eccentricity. We got this right out of the reference tables. And we basically decide, is it closer to 0 or is it closer to 1? And obviously this is very close to 0. So Earth's orbit is almost a perfect circle. Like I said, you'd have to have a really keen eye to be able to tell that difference. And where did I get that eccentricity? Well, I got it from the reference tables. I went to the Earth on the chart from the solar system data on page 15 in your reference tables. I look at the eccentricity, and that eccentricity is 0.017, and that's where that number came from. Now, if I bring up some of the other planets, we're looking at the terrestrial planets here. This is the sun right there. Then we have Mercury, Venus, Earth, and Mars. And if you look at Earth's orbit in blue here, 0.017 is the eccentricity. Here's the sun. I'll put the pointer right over it. You know, that blue circle for the Earth, that looks pretty darn close to a perfect circle. You really can't tell the difference all that well. But if I look at Mercury's orbit, which is a little easier to see since it's closer to the sun, you'll notice that the sun is not at the center. It's slightly off center, and that's because there's another focal point somewhere over here. And Mercury's orbit is much more elliptical, or much more eccentric. You could say it either way. When I look in the reference tables, look at Mercury's eccentricity, 0.206. That's much, much higher than the 0.017 that the Earth has. It's not as close to 0 for Mercury, and that's why it's more stretched out. You can also do a nice comparison between Earth's orbit and Mars's orbit right here, the Martian orbit. Notice the Martian orbit is pretty close to the Earth right here, but it's much farther apart over here. That means this is more oval shaped or more elliptical is the term we'd like to use than the Earth. And if I compare them, Earth's eccentricity is 0.017, Mars is 0.093. That higher number means it's more stretched out, more oval-like or more elliptical. And that's how we can use this calculation of eccentricity. Now, since the Earth's orbit is elliptical, that means sometimes we're closer to the sun and sometimes we're farther away from it. Now, again, very important to note, this diagram is not drawn to scale. We stretched it out drastically just to prove a point, because otherwise this would be hard to see. So here's our Earth's orbit around the sun, and we are closest to the sun, a point called perihelion, and that's a term you're going to want to know. Perihelion means we're close to the sun. Helios in Greek is the Greek word for sun. So anytime you see anything with helium, helios, any of that stuff, think of the sun. And it actually happens on January 3rd. So we are closest to the sun, 147 million kilometers away, on January 3rd, which is in the winter months for us in the Northern Hemisphere. And that defies a lot of people's logic. They're like, how can we be closer to the sun in the wintertime? But in reality, remember, it's the Earth's tilt that is the more dominant factor for our seasons. So actually, our winters would be a little bit colder if we were farther away from the sun than we actually are in the winter. So just this defies logic. You want to try to commit that to memory. And then we have another point called aphelion. Again, helion related to the sun. The easiest way to remember this, it starts with A. That's when it's farthest away. Try to commit that to memory. Aphelion starts with A, so it's farthest away. And this actually happens on the 4th of July. We're 152 million kilometers away. So 5 million kilometers farther away than we are on January 3rd. In space terms, that 5 million kilometers is really not a big difference. I know it sounds like a lot to us, but 5 million out of 147 or 152 is not a huge amount. Now, an aphelion, again, it happens in summer in the northern hemisphere because the Earth's tilt is more dominant than this distance factor is. And you also have to keep in mind that just because we're tilted toward the sun, the southern hemisphere is tilted away. So this actually works out for their winter. One of the hemispheres had to be farther away in summer, and it just happened to be the northern hemisphere. Notice it says this is when the sun would appear the smallest. Since we're a little farther away, it actually does have a smaller appearance in the sky. And it would actually look a little bigger in the winter since we're a little bit closer. And that's actually one of the ways astronomers realized that these orbits were not perfectly circular. So again, aphelion is when we're farthest away. If it starts with A, it's away. Perihelion is when we're closer. And we're closer in winter, farther away in summer in the northern hemisphere, which is opposite what you would actually think. So a little bit more on the Earth's orbit. This is just to kind of summarize what we were talking about. Remember, we said the sun is not at the center of the Earth's orbit. And that's true for the other planets as well. It's at one of the focal points, and that's an important term to remember. Aphelion is the point when the Earth is farthest away from the sun, and perihelion is the point where a planet is closest to the sun. When it starts with A, it's farthest away. Now, during what season in the northern hemisphere is the Earth closest to the sun? Remember, we're closest to the sun at perihelion in January, right around January 3rd, which is wintertime in the northern hemisphere. It is summer in the southern hemisphere. So if this was opposite, our winters actually would be a little bit colder and our summers would be a little bit warmer. So it actually kind of buffers things out for us a little bit. Now we're going to take a look at Kepler's second law. And this is where he starts to sound like a mathematician. Law number 2 says an imaginary line joining a planet to the sun will sweep over equal areas in equal periods of time. Now, if we put this into everyday language, it's a lot easier. This simply means a planet's going to travel faster when it's closer to the sun, and it's going to travel slower when it's farther away. So we brought back that kind of cheesy animation again, but it shows us what's going on. We've got the sun, the Earth, and Mars, and we're noticing that the Earth is revolving, at a much faster orbital velocity or speed in its orbit because it's closer to the sun, and that force of gravity is stronger, so it's whipping around a lot faster. Mars, being farther away, is going much slower. It has a longer path, and it also has to deal with less gravitational attraction, so it's moving at a slower speed. Now, law number 2 is also called the law of equal areas. So what we need to show you on this diagram is, again, we have this exaggerated diagram, not drawn properly to scale. What we have here is the point where aphelion, we're farthest away, and perihelion. Now, we know the Earth would be going fastest at perihelion because it's closer to the sun, and slower at aphelion because it's farther away. Now, what we're going to do is draw out some areas. If I draw area A here and area B here, since this is called the law of equal areas, what do I know about these two areas? Well, they are equal to one another. And you might say to yourself, what on earth does this matter for? Well, this is a mathematical way of proving that the planet goes slower here and it goes faster when it's at perihelion. Now, why does that prove that? Well, if this takes a month to go from here to here, it has to go a certain speed to cover that large distance in that month. It would actually go pretty fast to cover that bigger distance. But if it has a month to go from here to here and it's a shorter distance, it's going to go a lot slower as it goes across that shorter distance in a month than it would go if it has to go across that much larger distance in a month. And that's how you mathematically prove this. If that confuses you, don't worry about it. If you ever see a question like this, all you need to know is area A equals area B. They'll always be equal if they draw this out, and we'll do another example or two of this in the future. Now, Kepler's law, a third law, states that there's a mathematical relationship between a planet's mean distance from the sun and the time it takes the planet to revolve around the sun, which is known as its orbital period. So again, very wordy. Here's what it means in normal language. The farther a planet is from the sun, the longer it will take that planet to orbit. If the planet's closer to the sun, it will take less time for that planet to orbit. So again, diagram not to scale at all. We have our terrestrial planets, Mercury, Venus, Earth, and Mars. Then we have the asteroid belt. And then you get to your Jovian planets, Jupiter, Saturn, Uranus, and Neptune. And what they're basically saying is the planets that are closer to the sun are going to have a shorter orbital period. The planets that are farther away are going to take longer. There's really two reasons for this. The planets that are closest to the sun, one, they have a shorter path, much shorter, and two, they're going to be going faster because they have a stronger pull of gravity with them. The planets that are farther away, like Neptune, has a huge path to go around. The distance is much, much longer, and the force of gravity is weaker, so it's going to do it slowly. And if you remember, we said Uranus takes up 84 years to go around the sun just once, whereas Mercury takes 88 days. So it's a huge difference that we're talking about. Now, I'm going to start an animation here that's kind of cool to show you what this actually looks like. And if we start them all off at the same time, notice Mercury just completed an orbit, but Neptune is still going way behind here. And once they're all in motion, you can see how fast they actually go. So we'll let it run again. It's almost like watching track people running around the inside lanes versus the outside, except you're putting your slowest runners on the outside and your fastest on the inside here. And it really gives you an idea of how Kepler's third law works. It's also just kind of fun to watch and kind of mesmerizing too. So one more time, the planets go faster when they're closer, take less time to orbit, and they take a much longer time to orbit when they are farther away because they're going slower and they have that bigger path. So now we're going to take a look at a question just to make sure you understand that. If we have two planets, we have Earth and Venus, and again, this diagram is not drawn to scale at all, just a visual for us. Which planet will take longer to go around the sun? Is it going to be the Earth or Venus? And we want to explain our answer. So looking at the two planets, which one of these do you think would take the longest? Think about it for a second, see if you can come up with a reason, and then we'll tell you the answer. All right, so hopefully you had a second to think about it there. The answer is going to be the Earth will take longer. And why is the Earth going to take longer? Well, first of all, it's farther from the sun, so it's going to have a smaller force of gravitational attraction between the two, and that's going to make it go slower. And not only is it going slower, but it has a much longer path to go around to make that revolutional orbit than Venus does. Venus is closer, so it's going to be going faster because of the stronger pull of gravity, and it has a shorter path to go along. So we're going to go ahead and say the Earth simply because it's farther from the sun. Nice, simple way to answer that one. The final thing for us to do is bring kinetic and potential energy into the mix. Remember that kinetic energy is energy of motion. So the faster something's moving, the more kinetic energy it has. And potential energy is stored energy. A lot of times people think of an analogy of, if I were to pick up a rock and hold it above my head, I just gave it a lot of potential energy because it has the potential to fall back down to the ground when I let go of it. And that potential energy, once the object starts moving, will turn into kinetic energy. So if we have an object that's moving fast, which kind of energy would be more dominant? Would it be kinetic or would it be potential? Hopefully you said kinetic energy because that's the energy of motion. So the faster it's moving, the more kinetic energy you have. Now what we need to do is we need to connect this now to how does the energy, potential and kinetic, relate to the orbit of the planets. So let's go ahead and read the statements and then we'll take a look at it in the diagram up here. When the force of gravity is stronger, the object in orbit will move faster. And if it moves faster, it's going to have more kinetic energy. So wherever that planet or object, satellite, whatever you want to call it, wherever that is in the greatest speed, strongest gravitational attraction, that's where it's moving the fastest and has the most kinetic energy. When the force of gravity is weaker, that's when the object is farther away, the object will move slower, giving it more potential energy. The reason why it has the potential is that energy is basically stored and it has the ability to get pulled faster as it goes closer to the sun. So really, this is a visual thing. We need to see it. So we have an eccentric orbit here. It doesn't matter what these two objects are. I don't think it's drawn to scale. I don't think that's supposed to be the Earth there. If it was, it's not to scale. So we have this object, call it a planet, orbiting a star, in this case a blue star. Now here is perihelion. This is where the planet gets closest. Notice it goes faster there because the force of gravity is stronger when it's at this point. When it gets over here, it's farther away, so it's going slower because the force of gravity is weaker. Now when it gets to this point, now it's going fast, so that's the highest kinetic energy, and then that kinetic energy is being converted into potential. Now it has the most potential and stored energy, and then the potential energy gets converted back into kinetic as it goes faster, and we just go back and forth. More potential. When it gets here, it has its highest potential energy right here, And now the potential energy turns back to kinetic, and this is just a cycle that repeats over and over. You're not losing any energy, it's just changing from one form to another, and it's just going back and forth in a cyclic manner. So this will be our final question here before we go ahead and show you guys some animations in a different video. So looking at this, again, this is all exaggerated, not to scale. Let's say we have a planet and it's at position A over here and position B over here. So the question is, when the planet is at A, is it going to be moving faster or slower than when it's at B? Hopefully you said it's going to be moving slower because it's farther away. This would be the aphelion position because it's farther away from the sun. What kind of energy is going to be dominant when the planet is farther away and moving slower? Well, this is going to be your potential energy. It's got all that stored energy that can be converted back into kinetic energy. Now at location B, it's obviously closer to the sun, so it's at that perihelion position, which means the planet is moving much faster. And if it's moving faster, which type of energy is more dominant? Well, that's going to be kinetic energy. And again, it's a cycle where the type of energy just goes back and forth from potential to kinetic to potential to kinetic over and over and over and over again as these planets orbit the sun. All right, so that's basically our look at Kepler's laws. What we'll do in our next video is take a look at some animations to help you visualize it a little bit better.